Hello, my name is Ritesh Raj, and today I'll be presenting my analysis of algorithms project on the closest pair of points problem. Let's look at the problem definition and motivation. First, let me define the problem. Given a set of endpoints in a plane, we want to identify the 2 points with the smallest Euclidean distance between them. This problem is fundamental in mapping, robotics, and data clustering. To compare performance, I implemented two methods: brute force, divide and conquer. The experiments ran on an input size from 10,000 to 55,000 points, averaging each size over 10 trials. Let's look at the pseudocode and complexity. For brute force, two nested loops compute distance between all point pairs. For divide and conquer, I sorted the points by x and y coordinates, recursively finding the closest pairs in left and right halves. Examine a strip along the split line, checking up to 15 neighbors. And let's take a look at the experimental setup and tables. I generated random points with integration coordinates in 0, 3, 2, 7, 6, 7, and timed each algorithm in milliseconds. Two tables estimate the hidden constraint: ALG1 table for C n square model, ALG2 table, which is right here, for two for C and log n model, taking the maximum ratios given the constant C for each algorithm. Here, the graph one shows the empirical runtime comparison. The graph one overlays average runtime of both algorithms. The brute force curve rises sharply, illustrating quadratic growth, while the divide and conquer curve climbs more slowly, reflecting n log n behavior. And let's take a look at the graph 2, which shows the brute force empirical versus predicted. The graph compares measured runtime against predicted C(n) square values. The closest alignment confirms that the brute force algorithms follows O(n) square as expected. And the graph 3, which says about the divide and conquer, empirical versus predicted. This graph shows the measured runtime versus predicted C and log n values for divide and conquer. The convergence of two curves validates in O and log n complexity. And let me conclude by saying, in summary, the brute force approach is straightforward but becomes impractical for large data sets. The divide and conquer algorithm, though more complex, scales efficiently and aligns with theoretical predictions. This project demonstrates how asymptotic analysis reliability forecasts real-world performance. And this is the project demo, and here are the references. And let's take a look at the source code. Here is the source code. And here is my sample test case, which I've implemented. Thank you for your time.